Okay, now I'm back fully with you here. I think I have everything set up. So anticipating I was going to ask people if they have questions, and I see on the chat board here that indeed we have a couple. So John Robinson asked the question, for program 3, I've parsed through the file and know what the errors are. Should I state where they occur on top of what it is? So you're evaluating each line in the file one at a time. So what we're doing is, yes, oh, I see, you're saying where in the line that error is actually occurring. Any additional things that you can put in there is always better. Yes, it's not, I shouldn't say it's not required, because you have to at least be able to make it clear what you flagged as an error. So I'll leave that up to you as to how you actually identify that. Excellent. Other questions? So Aiden asked the question, looks like there's a conflict between the due date inside the PDF that I posted for assignment 3 and what is actually posted on Blackboard. I will give you till the 6th. I know I did state, I was originally thinking I wanted you to turn it on the 4th. That way you would be kind of directed to spend those extra days preparing for the exam. But with this new format, I don't think I need to worry about that. So if you want the time, I'll let you take the time and manage it. So the 6th is fine. That's what I said in Blackboard, and that's the absolute latest turn-in date. I do encourage you to turn in earlier so that you can really use that time preparing for final exams for all of your classes, including this one. So Kyle asked the question, so for my own program, I printed beneath each line whether or not that line was valid with the reason if it was incorrect. I prefer it to be on the same line. Once you start adding additional lines like that, sometimes it gets a little harder to track, but if it works for you doing it on the following line, that is acceptable. And Austin asked the question here, how is the final exam going to be formatted? And it's going to be a little bit different. It's going to be kind of like a combination, if you will, of the mini exam and exam number 2, the mini exam 3 and the exam number 2, because there will be some questions on some questions that will require you to write some code, and I'll be in my study guide very explicit about what that might look like. And in that case, you need the more free-formatted type of questions that you just saw in the mini exam 3, at least for one of the questions. Other questions? Looks like we're slowing down here. So one of the things that is obvious is that we already started with assignment number 3. We haven't had the official introduction to Lexers and Flex and Yak and all that yet. That's the topic for tonight's and Monday's lectures. So at this point, some of this you may have already dug into. You may have already read these files and used that to help you get started on the assignment, which is outstanding. Hopefully that's what a lot of people did. So the format now can be more like, really, do you have any questions about any of these materials that we posted to help you maybe understand it better? So bringing up the first file, six, where is that one? Oh, I see, because I have B up. Okay, let's do that. Okay. So in the first file, this one I labeled 6A is pretty much a high-level introduction to Lex and Yak, because I know a lot of you, I think, are really curious because you already had the assignment posted. You wanted to get into this, and you say, how do these tools work together? First off, what are they? How can I start playing with it? How can I get my hands in it? And then I want to learn about it more. I understand a lot of people like to do that, so I went ahead and posted 6A up here first, kind of to help those of you who want to learn it that way get a quick start. And so a couple things you need to know is that the input file for Lex is going to be a file with the .l file extension to it. And what it is it's a lexer. It's a scan. It's going to scan your input file, whatever is file.l that you're using to write your grammar with. It'll scan that, and then it's going to tokenize it. So what does that .l file look like? Okay, it's going to look like this screen here. You're going to have the percent brackets where you can put in some prototypes, comments, globals, things like that that you might be declaring. And if you don't, then that's fine. You can leave that blank. Then you have the definition section following that. And that's where you can do some substitutions that you want to be directly inserted into this file that Lex is going to generate. I should go back up to the top here and point that out, right? That, where's my pointer? There's my pointer. Come here, I want to change my pointer. There we go. Okay, so up here, right, we're going to take that file.l, we're going to run flex on it, or lex, and it's going to generate this file. Now, it might be tempting to go into that file, and it's actually very interesting to go into that file and see what it actually generates. But the thing you need to be careful about is that you can make changes in this file, and well, if you don't really understand the architecture of how this is going to get compiled and use your input for it, you can mess it up, and your results in code might not perform as you want to, which is why we're creating these sections here for being able to define our own code that we want to have included inside of this file here, that we want to use included for substitutions that we're going to base rules on. And then if we have additional subroutines that we want to go ahead and build, we can put it down at the very bottom of this file here and let Lex or Flex generate the source code file for you, because it'll put it in the correct place. It'll put the handlers for doing the calling functions in there correctly. It'll do all of that work for you, so you don't need to worry about inserting it in the correct place inside of this file that it auto-generates, and then you lose that the next time you run Flex anyway. So you really don't want to be hand coding this file, although I do find it interesting and encourage you to actually go through the file based upon what you did in your specification and be able to see if you can somewhat understand what's going on inside of there. It's pretty complex, but it's pretty amazing stuff as well. So yes, you can do your variables. you can do prototypes and comments up here, but then you can do your code substitutions here in this definition section. Now, the meat of this thing is between the pair of percents, and that's where we're going to define all of these rules that we want the scanner to use to read the input files that you're going to read, that you're going to give to this file that's being auto-generated that you would then compile. And that's where you do that, plus any additional code that you want Flex to generate inside of this lex.yy.c file. So what does the rules section look like? It looks like this. You're going to create some rules by building regular expressions, and that's going to help, that's going to define, that's going to tell this particular, it's going to define this particular grammar so that this particular code you're generating and the source code you're generating for this specification would then build a grammar based, build the scanner based upon the grammar that you have put into here. Now notice that we are building rules very much like the eBNF specification, right? Capital A through Z, lowercase a through Z, in this case, one through many instances. Now, the other thing you're doing is, in addition to the pattern, you're also going to specify what you want this tokenizer to do when it matches that pattern. So for an example here, you can do something very simple like this, where you're using, again, in curly braces as the action. We're doing the C function printf with something simple in there. So anytime we recognize a word, we're going to printf this is a word. All right, so going back to eBNF specification and how Flex is going to be implementing it, is that we're going to use these symbols here with these definitions. If we want to match any single character except for the new line, use a dot. 0 or more instances of the regular expression, star. 1 or more, plus. The equal sign is kind of fun because it says you can use exactly 0 or 1 of the preceding regular expression. So if you wanted to do recognize something that was only 2 characters, you could do the plus, the question mark, but that's not really what it's defined for. It's defined for more specific types of rules that you would build. The bar matches the preceding or the following regular expression. This or this, it's an OR function. And the square brackets can define a character class. The parens is a regular expression that it contains. And we actually use these ellipses to match everything within the parentheses as a literal function. So we use the ellipses to create a literal. So some examples here, if you want to recognize an integer and you do not want to have 0 as a leading integer value, because that's not really an integer, right? That might be a string that we can create that we can recognize, and it may be a formatted output if we want to do some formatted text, a formatted numerical text even. But typically with a number, it isn't preceded with a 0 unless you're doing something like a floating point number with a 0 and a dot, or a digit and a dot. But that's the bottom example. We're not there yet. So a true integer is going to start with a value 1 through 9. So we're going to do a single instance. Notice it's just the square brackets, 1 through 9, followed by 0, 1, or many instances of any of the other digits, 0 through 9. So we're done. Okay, so that's how we can then recognize a number like this. So Dante's asking the question about the ellipses. So if we use the ellipses, does that mean we can put anything in the quotes and that literal must be a part of the expression? Yes, that is true. That's what we're saying. All right, so now if we want to recognize a word like cat, and notice we are now reversing the order. The order doesn't matter. We're just saying the set A through Z lowercase, A through Z uppercase, and now the plus means we have to have 1, many, or more, right? Sorry about that. There was one thing I had to do. So yeah, preceding screen plus means we need to match one or more instances of the regular expression, which is differentiated from the asterisk, which is 0, 1 or more instances. And that's how we saw the difference here. So we can, using the plus here allows us to be able to accept a single character word like a, right? So that's a single character word. We need to be able to recognize a because we use that in sentences frequently. A or ah, you want to pronounce it that way depending upon the sentence that you're constructing. So that's why we would, in many cases, when we're defining a word, we want to be able to accept a single character word or longer. So that's why we're using all the chars and the plus symbol in this case. Now, of course, if we want to allow leet speak and some of these others capabilities, then we would include the digits as well. So you can do that, but typically words don't. So that's kind of a familiar definition of a word. Simply using those symbols. Any word you want to construct, well, using our language and our representation of our characters, it's defined this way. And bro, yes, your comment there is correct. If this had not been added to this A through Z lower, A through Z upper, and that plus symbol was not there, it was just the square brackets, like Bra had mentioned, it would only accept a single letter word. If we had used the asterisk, it would have been none, one, or many. And we don't want to accept a word that doesn't have any of these characters. So we want to use the plus. So going back up here to our definitions of regular expressions, the question was asked, what about the exclamation point? And we didn't define the exclamation point in the set of rules that Flex and Lex would accept. Okay, so any word that we want to construct, we would define a regular expression like this. A signed or an unsigned integer. Okay, now this is where we would use that question mark, right? So just as a reminder, a signed or unsigned integer would look like this as unsigned and this as signed. It could be the plus symbol as well, right? But if what we're really saying is we're going to accept an integer and we don't care if it's signed or unsigned. So in that case, we would define minus or plus, and then we would use the question mark because that could be no instances or one instance. Can't be more than one. It has to be strictly 0 or 1, none or 1. Okay, then followed by our definition of an integer, which we took from up here and just placed it after the question mark here. Then a floating point number will be constructed thusly. Here we would have 0 through 9 with the asterisk, right? Because as you recall, we could have 0 or more instances. And so that would allow us to be able to construct the floating point number without something in the ones place, like some people like to write. So you might want to choose to use a plus here, but since they want to, this particular example wanted to be able to accept a floating point number without, I mean, just in this case here, they're going to say 0, 1, or many instances of a digit, followed by the period, followed by 0 through 9, and now notice we use the plus symbol here, because if it's going to be a floating point number, we have to have at least one digit in the 10th column. Dante, thank you for the explanation there. Glad that helps. Okay, a couple of additional rules to think about when you're constructing your rules is that Lex, if it can classify what it's scanning with more than one rule, it will always choose the longest rules, the longest sequence that it can match, because it is deciding that if you built a rule that will accept and classify the first 3 chars that it's scanning, but you built this rule that's going to require 7 or 8 chars in order for it to be able to classify it, it needs to be able to meet that more sophisticated rule that you constructed in every case. And so that's why it will always take the longest sequence that it can use in a rule classification in the case of a multiple rule possibility for classifying a token. Okay, so you need to be thinking about that. This is why we're talking about these rules when you're constructing your rules, so that you can write them to be explicit in what it can accept based upon the length rule. Now, the other thing is a tiebreaker. If 2 or more possible tokens are the same length, then the first regular expression rule that you had defined is going to be the winner. Okay, so if you that's when you're constructing rules, the order will be important in the case of the same length can be accepted by 2 rules. Okay. Okay, you'll notice in the previous example that we included the parentheses in a couple of those examples. Okay, so one of the things that we are going to need to think about then is that when we are constructing some of our rules where there might be some ambiguity, then we will have to use the quotes to be able to explicitly state what we're trying to do. So that's really what we're saying in this slide here, where we're talking about delimiters, right? We have periods, equals, all of these symbols which have multiple meanings, right? So we can construct a rule such that we can accept the period, we can accept the question mark, followed by a asterisk. So we can, exclamation point. So we can use the quotes to help us define those symbols that have multiple definitions. Another thing we need to think about is like the C++ comment, right? We want to accept this pair of characters followed by 0, 1, or many instances of anything, because remember the period means anything. So the exclamation point is not a typo. It's because it's not ambiguous. It's not one of our built-in functions, if you will, for regular expression, for expressing regular expressions. There's no exclamation point there. So we can go ahead and just use that. White space is important, right? So if you want to accept white space, then you'll need to use the C syntax, like we have the /T, right, for tab. And then if we find 1 or more instances of these white spaces, we can accept them. And then of course we would want to classify them as white space. Or we might want to just pull them out and just do the processing. This is separating different tokens. Because at the process of tokenizing is going to take that input that we had to use the white space for the separation, so we could say, evaluate this as a token, then evaluate this as a token, right? Evaluate English as a token. I was waving my hands. I'm sorry, you couldn't see me waving my hands. So I'm back on the slide. So if I wanted to accept this as a token and accept this as a token, we had to have the white space separating the two so that we know that this is a break here. Evaluate this, classify this, classify this. In this case here, we still had the colon as part of this token here because this is the white space that broke this set of characters up from the next set of characters. So we need to be able to recognize white space so we can do that. So here's a way of building something to recognize and classify white space, but the difference is we can just remove the white space in this case. So now, let's see if you get your head around this then. We can accept and classify some sentence using English language by using this regular expression right here. So let's see if we understand it, right? We have the set of white space. The plus sign means what? One or more, right? Followed by, wait a minute, not followed by, there's the or sign. Could be white space, or it could be one or many instances of lowercase a through z, uppercase a through z. Oh, okay, so there's all the characters. And we can have 0, 0 or 1 or many instances of this. And we can have, we can also accept the period, the bar, the question mark, and the exclamation point. Or the exclamation point, excuse me. All right, so now we have basic punctuation that we can accept. And we have all the characters that we described before that we can accept. And white space. At this point, we can now accept this English sentence that we just saw up here. Okay, so that's basically what we're trying to do with the grammar. Let's see, Austin has a question about new lines and tabs. Anybody want to take a shot at that? So John's correct. So yeah, so if you want to accept other kinds of white spaces, like you were asking about, Austin, then you would need to include that as your set, that in your set, instead of a single kind of white space that it could accept, and include these other kinds of white spaces that you might want to accept. You might not want to accept a carriage return or a new line though. You might want to process that one differently, or you might not, depending upon what you're trying to accept. Okay, so that's our scanner. It's going to take your .l input file, generate the source code in C file lex.yyc. Now let's take a look at what Yak is going to do. So we built our scanner. Now we need to build a parser. And so that's what Yak is going to give us. And in GNU said it's Bison instead of Yak. And you do understand what a Yak is, right? Because remember, the whole Nutshell series of books are all famous for having different animals on the covers of the books. So Yak, of course, the animal is spelled a little bit different than Yak, our tool, but it's close enough. So they went ahead and called it Bison. Anyway, so what Yak is going to do is it's going to generate its own unique file. I'm sorry, it's going to read as an input its own input file, .y, .l for Lex, .y for Yak. Okay, so that's where we're going to define this, the grammar is in this specification file for Yak, which is going to be .y. What we're going to put in that file is the set of production rules. Okay, so the sequencing, just like we saw in our study of compilers, right? The sequencing is what we'll do in this phase of the compiler. And so that's what Yak will do. So it'll take as input some file .y, and then you'll run Yak on that file, and it's going to generate a file y.tab.c. So we have lex.yy.c, we have y.tab.c pairs of files from running Lex and Yak or Flex and Bison. Okay, specification for the Yak input file is going to be like this. Okay, here's familiar, right? You got the percent curly braces is where you can put your globals, prototypes, comments, just similar to what we did with Lex, followed by a definition section similar to what we did with Lex, where we can put any sort of declarations that we want to create or specify. We can do that here, and tokens that are recognized by the Lexer. Then, similar to the Lex specification, pair of percents. Pair of percents is where we put the production rules. Okay, this is how we're going to specify the grammar for this particular system that we're building. And if you want to include your own subroutines, additional subroutines, you would likewise do that here after the pair of percents of your production rules, and then it would generate the Bison, or Flex would generate the, Flex, but Bison or Yak would then generate the .c file, the y.tab.c file, using these rules, production rules, and any code that you want to put into here that you want it to be also generated as part of that. Okay, so that's the specification. That's what this looks like. Let's see what this might look like as in an example. Okay, so in the production rule set, we'll put the production rule and then the symbols it can recognize and the action to take. And that could be more than one. So we'll put the list here, and then it'll generate for that production rule this particular action. Now, the production rule can have conditionality to it. So if you have some symbols that you want to recognize and have it generate a specific action, you can do this. And then you can do the OR function to let it recognize additional symbols and take a different action on those. Or you could have just a single set of symbols on any production rules that generate one particular action. So you could do it with a single action, all symbols defined, or you can have conditionality to it. It's up to you. Okay, examples help. So let's start off with the simple one, a single recognition, a symbol. Let's say we want to recognize a statement, right? And a statement is going to recognize an expression, and if it recognizes an expression, then we're going to take this action. In this case here, we want to call the C routine printf, okay, with this escape code. And here, the $1 is the rule that produces it. It's going to be used as an input to printf. And if we want to build something more complex, then we can say, okay, what about an expression? Expression's a little bit more complex. So an expression can be defined as an expression followed by the plus, followed by another expression. In the example here, we're trying to recognize something like this, okay? And if we have an expression followed by a plus followed by an expression, then what we'll do is we will say, build these symbols put these symbols on the stack, and then use these as its argument. 1 followed by the plus followed by the 3, semicolon, that would be an expression. So that's 1, that's the plus sign. So we're going to use the OR to say, well, what if it's a subtraction? Well, then we would have an expression followed by a minus followed by an expression. And then we would use this first argument minus sign third argument, put that on stack instead. Or we need to be able to accept a single number. So we need to have a rule that accepts a number, in which case it's just one argument, puts it on the stack. Okay? So from this, we can build a parser to recognize this expression here, right? And it's going to do it in this manner. We have first argument is 5, classify that as a number. Number can be further classified as an expression. An expression can accept a plus, but you got to remember the order that we're evaluating this in. The order is going to be using a stack, which means what? So I kind of jumped ahead here a little bit on you, because I didn't introduce when I introduced Yak and Bison. I did not start off by saying, oh, by the way, it's going to use a stack to implement this. But I did start talking about a stack here when I was saying, let's put these arguments and push them onto the stack. So what kind of parser is a stack, uses a stack? Kind of one of those fundamental test question type of questions. Shift reduce parser, yes. Is that bottom up or top down? Excellent, so here we go. So we could evaluate 5 as a number. 5 can also be evaluated as an expression. An expression can be an expression followed by a plus followed by an expression, or it could be an expression followed by a minus followed by an expression, or it could be a number. So we did the number, we did the expression, but we only have the one number, so we can't evaluate it yet, right? So it needs to be another expression, which means it needs to be followed by a plus or a minus symbol, right? So we would have that with this symbol here, this plus. So this could be an expression, but it needs to be followed by another number. But we do have another number, 4. And if we were evaluating this left to right, and we didn't have any of this additionally here, then we could come down and say 4, we recognize and classify that as a number, we recognize and classify that as an expression, and now it can be classified as this expression, but we're not done. So we can't do that. We need to continue to evaluate. And so that's why we'll build this, we'll keep pushing things onto the stack here until we get all the way down to the last number, the 2, which we would classify as a number, classify as an expression. And it needs to have another number and a plus or a minus symbol in front of it. And so that's why this then rotates up to here. And 3 gets classified as a number, it gets classified as expression. Now we can classify this subcomponent into an expression. The number 3 followed by the plus, followed by the number 2. Then we're going to come and grab the minus symbol and say, oh, we need to build another expression. So we then reach out to that 4. which we already classified as a number. Now we classify it as an expression. Now we can say that's going to be further classified as at a higher level as an expression with the 4 followed by the minus followed by this expression that we already evaluated and classified. We could then take this expression, and now we can evaluate this expression because we already did this here. We did this symbol here. This expression now finishes this up. That finished up everything that we were evaluating on the stack. And we can now further evaluate this expression as a statement. And they come up here and say the statement is an expression, and then we print it. Okay, so we see how this works. Using stacks, you're continuously pushing things onto the stack until you can evaluate it. And using the using your shift reduce parser, like you mentioned, you would just continually use those tools to evaluate those tokens until you can classify it at its highest level. So Austin asked the question about Lex and Flex being scanners, yes, and Yak and Bisons are parsers, yes. So I mentioned, the reason why I mentioned Lex and Flex and Yak and Bison is because they are actual tools that exist. And you can use them interchangeably. They do the same thing. Lex and Yak are the classics. They've been out there. They're distributed with every Unix system, and some of the earlier Windows systems had some as well, and other systems had similar versions. And Flex and Bison are the versions that are produced by the GNU Foundation and provided by the GNU Foundation as part of the Free Software Foundation. So typically more people, and they're more mature as well and more widely used than Lex and Yak have been. So they kind of taken over, but we still refer to the all four pairs, the two pairs. It can be used interchangeably. Okay, so now that you got that, and I see you got that picture in your heads, you understand what we're doing with these tools. So now we want to put them together, right? So as an example, we can construct a simple calculator using these two specifications. And here's the specification for Lex, and here's the specification for Yak, as an example. Okay, so if you want to understand how these tools work, you understand how calculators work, this is a fantastic example, I think, to help you understand, right? So in the Lex specification here, this is where we're going to say we need to have this include file here, which means we need to construct this header file. And then we have the production rules between the pairs of percentages, right? And so now you know how to read these, right? You have to have a 0. You have to have the plus symbol means one or many, right? Okay, so yeah, you're right. I could go through this whole thing, but I don't need to because you now know how to read this, so you can evaluate this. Somebody had a question about the backslash. Dante had a question about the backslash. Actually, the backslash dot. I think I had a smudge on my screen. So right here, you see this instance of a backslash dot. And so his question is, what does that mean? So we saw a couple of other cases here, right? We had the plus symbol, which is defined as part of the specification. And then we have things like the OR function, which we talked about. And then we accepted other symbols with parentheses, but in this case here, we didn't say anything about the backslash dot example. So the backslash, but we have seen the backslash used previously, right? We did that with the backslash T, which in C means that's an escape sequence, right? So in the case of the dot, what does a dot by itself mean? Anything can go there, correct. So the escape sequence with the dot is a way for us to also capture the dot, the period, right? So if we want to have a real number, this is an alternative way for us to accept it. We could use the double quotes, but this is a better way to specify that. So if we want to have as an option a float or an integer, we can actually specify it this way. So Austin asked the question, well, is this how program 3 is going to look? Well, we're not building a calculator for program 3, so it's not going to look like this because these rules are different for a calculator than they will be for the grammars that you're building for the assignment number 3. Now, look at these two lines here, right? This is something we haven't talked about before, but we talked about, or showing you here in the curly braces, the yyLval.dval equals A2F. Oh, we know what A2F is in C, right? And then we have this YY text. Does anybody know what this is telling us? Yeah, A2F, ASCII to float of what comes out of YY text. Okay, so putting this together, so you would do this kind of a specification to get the numbers. You're reading characters, right? But we need a number. So in this case here, we're going to create a floating point number. And this is the function that we would use to create that with. And then we're going to classify that as a number. All right. Over on the Yak side, let's take a look at this. So in this case here, there's going to be this zcalc.h file that we want to include the specification for. All right. Now we're doing a couple of specific things that we want to accept here. Okay, so we're going to create tokens that'll accept names and numbers. We want to be able to classify something to the left as plus or minus and type it as an expression. Okay, so we're doing some of this work here that we said was optional, but we provide the mechanism for us to define a way to, going back here to our specification, going back here to be able to classify those definitions so the tokenizer can accept them. Okay, so that's what we're doing here. And then we go into our production rules. Statement list. Now it's going to be a little bit more, it's going to be a little different than what we saw in the previous example because that was a very simple case here. So we want to create a state, we want to be able to classify something as a statement list, a statement, or an expression. Okay, so this is how we would do it. And this is very similar to what we just walked through with the addition of a statement list where we define it to be either a statement or a statement list followed by a statement. Just that way we can construct something more, we can do operations on left hands and right hands, right? All right, and notice in this specification here, we need to include a main, okay? So you'll, in your Yak specification here, you'll need to include this where we're going to create a main, which is going to call yyparse and return 0. The yyparse function is the main function that either Yak or Bison will create or provide for you when it creates the source code to actually enter into these rules that it's created in this function here. That's the calling function. The results, and this is probably worth pointing out, the results of this work here, as you recall, is being put into this lex.yy.c source code file. Okay, so it's going to do that. It's not going to have a main, but all this is, what this is doing is creating those, the tokenizer for you so that you can either use Yak or Bison to generate the production rules, or you can build your own. If you just want a scanner to be able to scan input and provide these tokens for you, you can do that and then use those yourself. If you want to use them, use a tool to build that capability for you, then you would use the Yak or Bison, and in which case you would need to include the main there, and this is how it will then find this code here. You would provide that when you compile both of these together, and then it would be the calling function here, and you can only have one main. This is the code that's going to generate the main for us. So that's why you want to do that. Okay, so some great questions tonight. Dante asked the question, so our Lex or Bison files will always need a C-style main at the end? Typically, the Bison files will. Bison or Yak, of course, yes. You always want to do that. If you don't build a main there, then that means you're trying to build your own code generator at that point that wants to call this code that's being generated by Yak or Bison, which is doable, but it kind of gets away from what you're using Yak and Bison to do for you. Now, one thing I didn't mention in the question, and it's why are we using these tools instead of writing our own compilers? And the problem is, actually, the problem becomes very visible if you go through the GNU site and you look at all of the different types of hardware platforms that you can compile their code to generate. And that's one of the reasons why we have these systems tools like Lex and Yak or Flex and Bison, is to be able to say, hey, if somebody built a parser that will be able to scan this language input, and we have a version of Yak and we have a version of Bison that's available on all of these different hardware and operating system platforms already built, then we don't have to do that translation ourselves in our compiler. We do our rules, we generate our rules for our scanners, and we could tokenize those scanned input files. Then we can call Yak or Bison and perform those generation rules that we define for those systems tools, and those tools could then generate the actual part of that part of the compiler, and then we could go into optimization and the other stuff that we were talking about at that point in our discussions of compilers. So this allows us to take advantage of, hey, build it once, use it many times, right? And that is why we want to build systems tools, so that we don't have to recreate them for every different kind of language we want to define and provide to users. These kinds of system tools frees us up to build these different kinds of compilers that will operate on so many different operating systems and hardware platforms, and take advantage of the tools that we have, programming languages, and use those to generate the actual full WebAssembler at that point, or compiler. All right, so let's see, I guess 2 questions Seming Chang asked if this will be on the final or the assignment. There will be some questions about the generic Lexiac capabilities on the final. It will be in the study guide. I'll post that so you'll understand what we'll be looking for. And Dante, yes, this is correct. We want to use these systems tools to generate the parsers and the scanners for us. Because once the scanner is done, right, and the generation production rules are completed, what's left can come from any language, any of the different languages, and functional languages, in any of the different language types. You can, at this point, they were all meaningless. Those different kinds of languages and those very specific ones that we have, they're to help us create tools that are optimized for the types of solutions that we're trying to write for. All right, other questions? Okay, then I will go ahead and turn you loose, conclude this session, and wish everybody a fantastic weekend, and hopefully everybody stays safe and healthy. See you online. And thank you.